Today, we're diving into a massive, pretty much invisible revolution that's happening all around us, the creation of a truly smart electric grid. And, it all comes down to solving one enormous challenge, getting millions, and I mean millions, of different devices to all speak the same language. I know, it sounds a little like science fiction, doesn't it? But just imagine for a second, what if your electric car could actually negotiate the cheapest time to charge directly with a wind farm that's hundreds of miles away? Or maybe your smart thermostat could coordinate with all your neighbors' thermostats to prevent a blackout during a crazy heat wave. This isn't some fantasy, you guys. This is the future our grid is literally trying to build right now. But to get there, we've got to understand how the grid itself is changing. You see, the power grid we've all grown up with, that simple one-way street from giant power plants to our houses, is going through a complete and total transformation. It's becoming this dynamic, two-way superhighway of both energy and information. It's a whole new ballgame. Yeah, the grid is no longer just about those giant centralized power plants. Now it's about millions of new devices, and a lot of them are in our own homes, our own driveways. We're talking solar panels, EVs, smart thermostats, you name it. The experts call these distributed energy resources, or DERs for short, and every single one is a potential source of power, a place to store energy, or a way to intelligently manage demand. And this change, it is happening ridiculously fast. Just to give you some perspective, back in the year 2000, the US got 200 times more electricity from oil than it did from solar. But by 2018, that had completely flipped on its head. For every single kilowatt hour from oil, we generated almost 3 from solar. That is an absolutely astonishing shift in a really short amount of time, and our old grid just wasn't built for that kind of world. So, with millions of new devices popping up and coming online, how in the world do engineers and operators even begin to make sense of all this? How do you manage this new, incredibly complex world without it turning into total chaos? Well, like any good explorer, you start by drawing a map. And probably the best map we have comes from the National Institute of Standards and Technology. You might know it as NIST. So instead of looking at the grid as just one giant messy thing, the NIST model breaks it down into these key functional areas they call domains. Let's just take a quick tour of the 3 most important ones. First up is the generation domain. This one's pretty simple. It's where electricity gets made. Now, traditionally, that meant a handful of massive power plants. But today it includes everything from huge wind farms all the way down to the solar panels on our own roofs. Okay, next, that power has to travel through the transmission domain. I want you to think of this as the interstate highway system for electricity, these huge high-voltage lines that carry massive amounts of power over really long distances. And finally, we get to the distribution domain. So if the transmission lines are the highways, these are the local streets and roads that deliver that power for the final mile, right to our neighborhoods, our businesses, and our homes. This is where the grid actually touches our daily lives. So we have all these different domains and millions of new devices, but for them to work together as one big, cohesive system, they need one absolutely crucial thing: interoperability. Now, I know it's a bit of a technical term, but the idea is actually really simple. It's not enough for 2 devices to just send data back and forth. They have to understand each other. They have to be able to actually use the information they exchange. And that right now is a massive problem. Our so-called smart grid is basically an electrical Tower of Babel. Just picture it. You've got a solar inverter from one company, an EV charger from another, and a battery system from a third. They're all incredibly smart on their own, but they were all built using their own private closed-off languages. They can't coordinate, they can't work together, it's a mess. I mean, just look at this diagram of a grid with a lot of those DERs. This is the reality. It is a chaotic spiderweb of communication pathways, all of which are needed just to keep the grid stable. We're going from a simple top-down system to this complex web where literally everything needs to be able to talk to everything else. So how do you fix this? How do you tame the Tower of Babel? Well, you don't try to teach every single device 100 different languages. No, that'd be impossible. You create one universal language that everything can speak, a common standard. And that language has a name, IEC 61850. It's an international standard that was actually decades in the making, and it was designed specifically for power utility automation. So think of it as the universal translator for the grid, the thing that allows equipment from any manufacturer to finally understand each other. Perfect. Now, the genius of IEC 16850, and this is really clever, lies in its 2-part approach. First, it defines the what. It standardizes the meaning of the data into a universal dictionary for all grid equipment. But, and this is so important, it separates that from the how, the communication method that's used to send it. This is a total game changer. It means as technology evolves, from Ethernet to 5G to whatever comes next, the core language stays exactly the same. The standard is designed to last for decades. It's basically future-proof. So what this does, in essence, is create standardized digital labels or name tags for everything. Every single circuit breaker or transformer on the grid gets a standard name and a standard data structure. And that means any other device on the network automatically knows what it is, what it's doing, and how to talk to it. No custom programming, no headaches. And this universal language makes the biggest difference inside the nerve centers of the grid, electrical substations. These are those really complex hubs that step voltage up or down and route power exactly where it needs to go. And inside a substation, communication has to be flawless and pretty much instantaneous. A really key part of the standard is a type of communication called a goose message. Goose is reserved for the most urgent, time-critical information you can possibly imagine. We're talking about a command telling a circuit breaker to open up to prevent a fault from cascading into a widespread blackout. These are the get out of the way, this is an emergency messages of the grid. And just how fast is that? Well, the standard demands delivery in just 3 milliseconds. That's 3/1000ths of a second. To put that in perspective, a blink of an eye takes about 300 milliseconds. That's 100 times slower. This is a level of speed and reliability that it was unthinkable with the older systems. Okay, so we've got this incredibly powerful, ultra-fast, universal language for power grids, and it's a fascinating piece of engineering for sure. But why does it matter to you in your day-to-day life? What's the bottom line here? Well, ultimately, all of this technical stuff translates into some major real-world benefits. An interoperable grid is a more reliable grid, period. It can react in milliseconds to prevent outages. It means we can seamlessly integrate enormous amounts of wind and solar power without crashing the system. It leads to more efficient operations, which means lower costs for utilities and, more importantly, for us. And it opens the door for you to participate, letting your smart devices actually help balance the grid and save you money in the process. When you step back and look at the big picture, what this all means is that we're no longer just building an electrical network. We're building one of the largest and most important computers on the entire planet. It's a computer made of power lines and solar panels and electric vehicles and smart devices. And with standards like IEC 61850, we're finally writing the operating system for it. So the only real question left is, are we ready to program it for a cleaner, more reliable, and more efficient future?